ever tried pushing a heavy door open by pressing your hand right next to the hinges? You have to push incredibly hard, and it barely moves. But move your hand to the opposite edge near the handle, and the same door swings open with ease. That difference in difficulty has nothing to do with human strength. It is entirely determined by the physics of turning forces, rotates, known as the pivot. Let's say you push the handle edge with a force of 40 newtons. To find out exactly how much turning effect you are generating, we use a simple mathematical formula. The moment equals the force applied multiplied by the perpendicular distance from the pivot. If our door is 0.8 meters wide, we multiply our 40 newtons by 0.8 meters to get a moment of 32 newton meters. Now, here is where many physics calculations fail. Distance must exclusively be measured from the pivot. You never measure from the swinging edge or the middle of the object. Always start exactly at the hinge. Because distance acts as a direct multiplier in the formula, maximizing your distance from a pivot is the most effective way to turn any object. Let's evolve this single moment concept into a balanced system. Think of two children of different weights trying to balance perfectly on a playground seesaw. To keep the board level, the lighter child sits further back, while the heavier child scoots closer to the center pivot. We can see the exact mechanics of this in the diagram here, showing a wooden meter rule balanced perfectly on a triangular pivot, exactly at the 50-centimeter mark. This is the principle of moments. For any body to be in perfect equilibrium, the total clockwise moments must equal the total anti-clockwise moments. Watch what happens if a 10-newton weight lands precisely on the 10-centimeter mark. The ruler instantly tips out of equilibrium. So, where exactly must a larger 20-newton weight be placed on the opposite side to restore perfect balance? Pause the video and calculate your answer. Let's break down the left side calculation first. The distance from our 50-centimeter pivot to the 10-centimeter position is 40 centimeters. Multiply that by our 10-newton force, and we have an anti-clockwise moment of exactly 400 newton centimeters pulling the left side down. To balance the system, the right side requires an equal 400 newton centimeters of clockwise moment. We divide that 400 by our 20 newton force to get a required distance of 20 centimeters. Adding that 20 centimeters to our 50 centimeter pivot point tells us the weight must land precisely on the 70 centimeter mark. Physical balance is not achieved by having equal weight on both sides. It is achieved by creating mathematically equal turning moments. In the real world, we rarely calculate single, isolated point weights. We must account for the distributed mass of entire, complex objects, with gravity pulling down on every individual particle. To simplify this, engineers use the concept mapped out in this diagram, the center of gravity. The intersecting lines converge at a single theoretical point where the object's entire weight appears to act. A common misconception is that this center of gravity must be located inside the physical material. For shapes like a hollow tire or ring, the center of gravity exists perfectly in the empty space in the center. Locating this point is essential for predicting how an object will behave when tilted. If you know where the weight is concentrated, you can calculate exactly how far a shape can lean before its own weight causes it to tip. Let's apply these principles to a high-stakes scenario. Local matatus, or public taxis, navigating sharp corners on Ugandan roads. This diagram shows a cross-section of a safely loaded taxi rounding a curve. Because heavy luggage is placed low to the floor, it maintains a low center of gravity. Notice how the vertical downward arrow representing its weight points securely between the rear wheels. Now contrast this with a dangerously loaded vehicle. Here, the heavy items are piled high on a roof rack, which elevates the center of gravity. As they round the corner, both vehicles tilt by the same degree. Watch the mechanics of a topple. Because Taxi B's center of gravity is so high, as the vehicle tilts, the downward weight vector eventually pushes outside the vehicle's wheelbase. Once the weight falls outside the base, the outer wheel acts as a pivot. Gravity now creates an unbalanced clockwise moment pulling from that high center of gravity, causing the vehicle to flip over. These outcomes are governed by the mechanical rules in this grid. Calculate moments precisely by measuring from the pivot. Maintain equilibrium by matching clockwise and anti-clockwise moments, and increase stability by using a wide base and a low center of gravity. Mastering these physical laws explains why a well-loaded vehicle stays grounded while another topples. Whether you are loading cargo or balancing a simple tool, These calculations define the practical difference between a stable system and a dangerous one.